What is the source of the sun's light and heat? Throughout history, people have proposed answers to this question that have always reflected human experience. The sun was a shining god, or a spark, cast off in creation. Later it was a pile of burning sticks or coal. By the 19th century, astronomers had become accustomed to thinking that gravity was the dominant force in the heavens. So they began to conjecture that the energy of the sun might be due to gravitational collapse, a compression of solar gases by gravity. This simple hypothesis, its proponents claimed, could provide the required energy output for a few tens of millions of years. By the late 19th century, however, geologists were confident that Earth was much older than the astronomers' model would allow. And the conflict between astronomy and geology continued for several decades. Then in 1920, the British astronomer Sir Arthur Eddington combined the principles of gravitational collapse with an exciting new principle in the physical sciences, nuclear fusion. He proposed that at the core of the sun, pressures and temperatures inducted a nuclear reaction, fusing hydrogen into helium. In 1939, two astrophysicists, Subrahmanyan Chandrasekhar and Hans Bethe, working independently, began to quantify the gravitational collapse and nuclear fusion hypothesis. Bethe described the result of his calculations in a brief paper entitled Energy Production in Stars, published in 1939. The model that followed the work of Eddington, Chandrasekhar, and Bethe described a nuclear furnace responsible for igniting stars. And for decades now, cosmologists, astronomers, and astrophysicists have accepted the basic concept as fact. In the early formulations of the standard model of star formation, it was said that the gravitational force within a primordial cloud leads to its progressive compression into a circumstellar disk, as the outer material in the cloud falls inward and gravity gives birth to a star-sized sphere, whose core temperature continues to rise under increasing pressures. Collisions of atoms within the core eventually become so energetic that electrons are stripped from their nuclei, leaving free electrons and hydrogen protons. A plasma as we now understand it. In stars roughly comparable to our Sun, we envision core temperatures less than 15 million Kelvin. The nuclear reaction begins when hydrogen protons are joined or stuck together in the proton-proton fusion of hydrogen into helium. Critics, however, pointed out that the temperatures given by standard gas laws are not sufficient to provoke nuclear fusion. They cited the Coulomb barrier, in this case the electric repulsion between two protons, or like charges. Once protons are fused, they could be held together by the strong nuclear force, but that force dominates only at short distances. To achieve fusion, it would be necessary for protons to cross the barrier of the repulsive electric force, which is sufficient to keep the protons apart forever. But Eddington's successors accomplished the impossible by something called quantum tunneling, enabling an extremely small percentage of protons to simply appear inside the barrier at any particular time. It's ironic that the early objections to the fusion model of the Sun focused on the powerful electric force. This was long before the arrival of the space age, with its discovery that charged particles of plasma permeate interplanetary and interstellar space, and long before any systematic investigations of plasma and electricity in space. Advocates of the nuclear furnace made a series of fundamental assumptions common to astronomy long before the emergence of the nuclear model of the Sun. The credibility of these assumptions was not an issue to them. They assumed that diffuse clouds of gas in space would collapse gravitationally into star-sized bodies. They assumed that the Sun's mass could be calculated simply from the orbital motions of planets. They assumed that Newtonian calculations of mass, coupled with standard gas laws, enabled them to determine the pressure and temperature of the sun's core. The pioneers of the nuclear furnace also followed another assumption common to astronomy in their time, that the sun and planets are electrically neutral. They gave no consideration to the role of electricity and no consideration to the role of magnetic fields that electric currents generate. Are the assumptions made in the first half of the 20th century still warranted after decades of space exploration? Those proposing an electrical perspective, based on more recent data, insist that the earlier conjectures are not only unwarranted, but discredited by direct observation and measurement. They emphasize that every feature of the sun, as we now observe it, defies both the gravitational assumptions and the standard gas laws relating to pressure, density, temperature, and relative motion of gases. The deepest observable surface of the sun yields a temperature of about 6,000 degrees Celsius, or 10,300 degrees Fahrenheit. As we peer into the darker interior of sunspots, we see cooler regions, not hotter. But moving outward to the bottom of the corona, the temperature jumps spectacularly to almost 2 million degrees Celsius, or 3.6 million degrees Fahrenheit. Thus, the superheated shell of the sun's corona reverses the expected temperature gradient predicted by models of internal heating. It seems the sun doesn't even respect gravity. The mass of charged particles expelled by the sun as the solar wind continues to accelerate beyond Mercury, Venus, and Earth. Solar prominences and coronal mass ejections do not obey gravity either. Nor does sunspot migration, nor does the movement of the atmosphere, since the upper layers rotate faster than the lower, reversing the situation predicted by theory, while the equatorial atmosphere completes its rotation more rapidly than the atmosphere at higher latitudes, another reversal of predicted motions. If the sun's atmosphere were subject only to gravity and the hot surface, it should be only a few thousand kilometers thick instead of the hundreds of thousands of kilometers or more that we measure. Even the shape of the sun defies the expectations of theory. The revolving sun should be an oblate sphere, but it is a virtually perfect sphere, as if gravity and inertia have been overruled by something else. For the electrical theorists, that something else should be obvious from the dominant observed features of the sun, in contrast to things assumed but never seen. The anomalies facing the standard model of the sun are predictable features of a glow discharge,